sklearnmetrics balanced accuracy score. Description: the balanced accuracy is a metric for evaluating the performance of a classification model. Particularly useful when dealing with imbalanced datasets. It addresses the limitations of traditional accuracy by considering the proportion of correctly classified instances in each class. It is calculated as the average of recall obtained on each class. Inputs: Y true. This input represents the true labels of the instances, provided as a 1D array of integers or strings. Each element in the array corresponds to the true class label of the corresponding instance in a dataset. YPRED. This input represents the predicted labels generated by the classification model. It is also provided as a 1D array of integers or strings, with each element representing the model's prediction for the corresponding instance. Outputs: balanced accuracy. This output represents the balanced accuracy score, a floating point number between 0 and 1, indicating the model's performance. A score closer to 1 indicates better performance, while a score closer to 0 indicates poor performance. Steps: calculate the recall for each class. Recall is the ratio of correctly predicted positive instances to the total number of actual positive instances in that class. Calculate the average of the recalls across all classes. This average represents the balanced accuracy score. Metrics: balanced accuracy. This is the main metric calculated by the balanced accuracy score function, representing the average recall across all classes. It is a valuable metric for assessing the model's performance in scenarios with imbalanced datasets. Recall: this is the metric used to calculate the balanced accuracy score. It measures the ability of the model to correctly identify positive instances in a given class. Visualization plots. Confusion matrix. This plot displays the predicted versus actual labels for all classes. It provides a visual representation of the model's performance on each class. Precision recall curve. This plot visualizes the trade-off between precision and recall for different classification thresholds. It can be helpful for evaluating the model's performance across various thresholds. ROC curve. This plot illustrates the model's ability to discriminate between positive and negative instances. It shows the true positive rate sensitivity against the false positive rate 1 specificity at different thresholds. Fine-tune parameters. None. The balanced accuracy score function does not have any fine-tune parameters. Uncertainty methods. Confidence intervals. You can use bootstrap resampling techniques to estimate the confidence intervals for the balanced accuracy score, providing a measure of uncertainty around the estimated performance. Bayesian methods. Using Bayesian inference, you can incorporate prior knowledge about the model's performance and obtain a distribution of possible balanced accuracy scores, allowing for a more nuanced understanding of the model's uncertainty. Challenges and fixes. Challenge 1: data imbalance can significantly impact the balanced accuracy score, as a model may perform well on majority classes but poorly on minority classes. Sample use case that resulted in challenge 1. Imagine a dataset where 90 of instances belong to class A and 10 belong to class B. A model that predicts all instances as class A would achieve a high accuracy but would have a low balanced accuracy, as it completely fails to identify instances of class B. Fixes to challenge 1. Data resampling techniques like oversampling, duplicating minority class instances, or undersampling, removing majority class instances can help to balance the dataset. Cost-sensitive learning. Assign different costs to misclassifications based on the class imbalance, forcing the model to pay more attention to minority classes. Challenge 2. Imbalanced datasets might lead to biased models, favoring the majority class. This can be observed when the model predicts the majority class for almost all instances, resulting in high accuracy but poor balanced accuracy. Sample use case that resulted in challenge 2. Consider a scenario where a model is trained to predict whether a customer will purchase a product. The dataset is heavily skewed towards customers who do not make purchases. A model might learn to predict no purchase for most instances, achieving high accuracy but failing to identify potential buyers. Fixes to challenge 2. Use appropriate evaluation metrics like balanced accuracy, F1 score, or AUCROC to assess the model's performance considering class imbalances. Implement strategies like class weighing or cost-sensitive learning to guide the model towards better performance on minority classes. Choose algorithms specifically designed for handling imbalanced datasets, such as XGBoost or LightGBM, which offer built-in mechanisms for addressing class imbalance.